Let's start, colleagues. Welcome to this JBS and Eflows training session. As you are aware, we are going to have these training sessions. We are going to have these training sessions every Thursdays from 9 o'clock to 10:30 the whole of February. So we are going to have 4 sessions, and this is the first session that we are going to have. Just to let you know that Prof. Gordon has requested to switch session today he would do session 1 and 2, to switch session 1 and 2, and today he will start with the introduction and biological components, and next week he will do the physical components. So this is the slight amendment that has been made to our agenda. So without wasting time, colleagues, let me hand you over to Prof. Gordon. Over to you, Prof. Gordon.
Thank you, Zviko. Good morning, everyone. I know that some of my guys are still struggling to get in, including one of my presenters. So Dr. Van der Waal, same issue. It seems that, Zviko, it seems that the link seems to be kicking some people out. You don't have I don't know why it must be them, because I mean, there's so many of us here. Yeah, Bradley's admitted. Zviko, could you send just on an email to me, if you don't mind, because there's at least 2 people still, just the link, not the invite, just the link to me directly. And then that might solve the issue, if you don't mind, just separately. Zviko, can you hear me? Zviko, can you hear me? Can anybody hear me?
Yes,
yes. Oh, there we go.
Yes,
I can hear you.
Okay, great. Could you? Yeah, thank you very much. Because then I'll quickly just send it on to a few of the guys who are struggling. Thank you very much. Great. So, guys, colleagues, it's really good to get together again. Thank you for attending these sessions. A lot of what we're going to do now, we had intended to present to you while we were in Gaborone and in Bulawayo and in Chokwe, and we didn't have the opportunity to do that. So we're taking the opportunity now with both hands to present this information to you. We think this will make a massive contribution to your understanding of what we do with the information. Bear in mind, please, that we have a broad audience that have varying interests and technical training with different levels of technical skills. So we're trying to pitch this to the whole community. But if you, there it is now. Thank you, Zviko. But if you have any questions, please don't be shy. We definitely want to make sure that we can get as much out of these sessions as possible. So please ask your question. Just stop. I might not be able to see your hand if you. Thank you, Zviko. Sending it on quickly. And one more. Here we go. Let's give it a go. Okay. Hopefully that'll work now. Thank you very much. There he is. There he is. Okay, so I'm going to just start a presentation. There are a few of us who are presenting today. I apologize for changing the structure somewhat and late notice that we're going to change the sessions, but we actually it's actually a natural requirement that we have to present different aspects together. We realized that was actually the problem. We also have some of our group who are still collecting some of the last little bits and pieces of information that they need for their presentations. So we've staggered that a little bit. Can you see my presentation?
Yes.
Yes.
Okay,
Yes.
fantastic. So we'll get started. So again, hello everybody. It's wonderful to see all of you here again, or to see at least your names and to know that you're there. We've missed you over the last couple of months, and we hope to get the chance to see you in person again in the future. So we have, as Zvika mentioned, 4 training sessions this month. This is the first of the 4 today, and yeah, I'm going to present the different sessions in a moment. But I wanted to start with, again, just to look at the terms of reference for the study. And we have 3 outputs and 3 important components. The first is to contribute to the technical capacity development of stakeholders in the Limpopo Basin. That's all of the countries. And your ability to understand what it is that we do when we do joint basin surveys to determine the present ecological state of ecosystems, and then to determine the environmental flows. And I want to throw it out there now is, has anybody ever asked the question, and I hope you know the answer to this, but I think we want to raise this for a little discussion at the end. Why is it that we do present ecological state assessments? And why do we do environmental flows? And how is the knowledge of the present ecological state of an ecosystem, a river ecosystem, and the environmental flow requirements used? Well, how can that contribute to the way that we manage our water resources towards sustainability? So that's a question just to throw out in the beginning, and we're going to come back to that at the end. We then have a joint basin survey component of the study, as I mentioned, to determine the present ecological state of rivers across the basin. And that gives us an indication of how the rivers in the basin are doing today. Okay, so I need to emphasize the importance of, we are trying to determine the present ecological state. And this raises the second important question. Why is it important to know what the rivers look like in the past compared to today, and on occasion, where they're going in the future? Why is it important to do that? And then finally, we have an environmental flow component in the study. In South Africa, we refer to this as the ecological reserve, the water required to maintain our ecosystems and meet the basic human livelihood needs of South Africans. For the rest of the basin, environmental flows, using the definition of environmental flows in its strict term, is the amount of water required to maintain ecosystems so that they then in turn contribute to human livelihoods. Okay, so South Africa's ecological reserve is the environmental flows and basic human needs. And again, what is it that we're interested in? We're not looking at the water in the environment. A lot of people think that environmental flows means water in the environment. We're looking at the amount of water needed to maintain those ecosystems. And when you, again, if I look at why is it important to consider the past and the present, because we need to know what the systems need to maintain it in its natural condition relative to how things are changing today. And what I mean by that, just to further explain that, is when we determine the environmental flows, we don't use the present ecological state to determine environmental flows. We do look at the present state to look at how much the system has changed and how resilient the system is to changes. We also look at what's in the system today as ecological indicators, but we actually want to provide the flow requirements and for the organisms that were there in the past, so that the systems, what the systems look like, could become sustainable. And in many parts of the world, you'll be surprised to hear that we are in a surplus or a sufficient supply of water to meet the environmental flows. That's what we've experienced across Africa, is that there's enough water to meet the environmental flows. And then on occasion, which is the case in the Limpopo Basin, we realize that we have actually most probably overutilized our water resources, and the environmental flow requirements are greater than what we're experiencing currently. Okay, so keep that in mind as well. And we're going to get to all of this as we go. So again, just in terms of the objective for the training, it's to help you understand what we're doing and help give you an opportunity to engage with us, so that we can optimize the process and not only determine the present ecological state, but how you can use that information, determine the environmental flow requirements, and ecological risk assessment framework to understand the socio-ecological consequences of altered flows, including the environmental flows, so that you can then contribute to your water resource management going forward. So based on those three objectives, in this slide, you can see we're proposing, just going to put a laser pointer up, the technical capacity development, joint basin survey component, and environmental flow objective. And where are we today? We're in 2025. We haven't completed all of the surveys that we had hoped to complete because of water availability in the Chongan and Basin National Park. We also knew that we would need to go back to spend more time in the lower Limpopo floodplain and estuary, and we're planning to do that early this year. And hopefully after that, we'll be able to catch up with our environmental flow risk assessment specialist workshops. And this year, we're going to report on the present ecological states, but we're also going to focus on the environmental flow determinations. So again, just to give an idea as to where we are in the study. I know that, and I want to just acknowledge that LIMCOM team have raised the possibility of a joint basin survey 1.5, and that is being discussed. We also know that and encouraged your opportunity to come and see us when we're looking at the floodplain and the estuary. So we hope to see some of you in the field. And the feedback and the contribution to your understanding of what we're doing in the study is not going to end today. Okay, but that's what we're focusing on here, is the capacity building component towards the capacity building plan report. So as I mentioned, there are 4 sessions this month. I've changed the title slightly for today towards where, and it's what the title of today's session is, towards the present ecological state determination of rivers in the Limpopo Basin, part 1. Next week, we're going to have part 2. So I'm not splitting it up into physical and biological components. We're going to do both, integrate both. We're going to do 1 session today and a more focused session next week on the biological and physical indices and applications methods that we use. Then on the 20th of February, we're going to shift towards environmental flows and the relationships. Why do we need to go into the field to collect data in the field, and what do we do with that information, and how does that contribute to our environmental flow determination? And that flow ecosystem relationship component that we can only determine through evidence that we generate in the field is paramount. And then the last session this month will be to look at prop flow and how we use all the information to generate not only the environmental flow requirements, but then also to develop an ecological risk model framework for you to look at the consequences of altered flow, so that you know when where we are today and what are the consequences of the scenario that we're experiencing today. If you implement environmental flows, what are the socio-ecological cost benefits of that implementation? And or if we go through severe droughts and future climate scenario problems, what will the potential risk to the people and the environment be? So we plan to give you as much information as possible to make a real contribution to the way that you're managing water resources, not only in each of your countries, but on a transboundary scale. And don't forget, what the first time that we're really focusing on the study is to show you how from source to sea you're connected, and what happens upstream affects people downstream, and from a fish movement perspective and other ecological attributes, what happens downstream, like barriers, for example, affects people upstream. So today we're going to have quick introductions. We're not going to go through everybody, I'm afraid. What I just wanted to do is I wanted to introduce you to myself. So my name is Gordon O'Brien. I represent Rivers of Life, which is a research program based here in South Africa. I am an associate and work with the universities, Northwest University and the University of Mpumalanga in South Africa. And I work for, as well, a university in Australia called Charles Sturt University. So our program is Rivers of Life. We're based here in the Lowveld, in Mbombela, close to the Mozambique, not so far from the Mozambique border. We're in the basin. We've worked in the basin for a lot, or the Nkomati and the Limpopo for since the monograph in 2009. We've been involved in this type of work, which has been really special. And I thank you for that. Today, Dr. Benny van der Walt is going to present on geomorphology. And then Angelica Kaiser, who most of you have met in the field, is going to present on some of her fish work. If we have time, and I'm sure we will have time, I will present some of Bradley, our invertebrate ecologist's work. Bradley is a scientist from the biodiversity company, but he's also joining our group as a PhD candidate this year. So that's who we are today. And then next week, we're going to have part 2, which is the rest of the team will present a part of their components. We won't have the introduction next week, so we'll have a lot more time to go through water quality components, hydrology components, and then the riparian vegetation component next week. Today, we're going to look at geomorphs, as I said, fish and macroinvertebrates, and then we'll talk about the rest of the meeting. But we're going to start with an overview and the determination of the present ecological state of water resources. Whatever we do in science is driven by best practice developments globally. And I want to use that as my opening argument, because whatever you do anywhere in the world, we have certain philosophies that drive or direct the approach that we take. And as scientists, ecological scientists, we have our own scientific philosophy, which requires you to use the best of the best and to contribute to the best of the best. And this review that was undertaken in 2023 presents a review and a really robust argument as to how to approach river health monitoring globally. Okay. And what was really nice about this, I had the opportunity to contribute to this paper, and so did Dr. Chris Dickens, who are both South Africans. And one of the important outcomes here was to show how globally river monitoring has developed from the 2000s primarily to 2020, and how different countries around the world, including the South African River Ecostatus Monitoring. And I just wanted to add here that what was not included was the 1997 development and establishment of the South African River Health Program. And because there were a lot of teething processes, there was a lot of new methods coming in and being used in and out. It wasn't, there was not a formalized structure until later on. And that's why the reviewers argued that we should remove that. But just to highlight that from our region, we have had very valuable initial contributions to river health monitoring in the 90s. And that foundational work has contributed to what we're doing today in the region and the rest of the continent and around the world. So many of these developments around the world have used a lot of the Southern African methodologies that have been developed. What's also very valuable from the paper is to identify the importance of scale. And what we're looking at here, and this is something that has been acknowledged in this paper, is the importance of these different indicators, biological indicators, physical indicators, water quality and flow, for example, and how you can determine that on a site scale that can contribute to the determination of the present ecological states of rivers on a subcatchment scale. And we need to work towards upscaling that information towards understanding how rivers are doing globally. And that's where the science is. So the reason why I wanted to show you this was for two things. First of all, South Africa has been making a major contribution to the methods that we use, not only across the Southern African continent, but around the world. And these methods are recognized as robust approaches to river monitoring. But the field is at a point where we'll all understand the need to start to share information and work together towards understanding the river health of our systems on a larger continental and global scale. This is just to show you basin scale, which is what we're doing, and then a continental scale. And there's a lot of effort going into developing that at the moment. And that's where we are. So I just wanted to highlight that, again, the foundation of the methods that we are using with some developments have been established through the River Health Program and the River Ecostatus Monitoring Program of South Africa. And those methods are used widely across the continent, even as far up as the Nile Basin. A lot of these methods are used. This figure, if any of you know me, I love this figure because what we always try to communicate to stakeholders is how we're all a part of these interconnected dynamic systems. So our river and natural environments are complex. They're dynamic. I'm just going to take that away for a moment to have you focus on this picture. They are dynamic and complicated, but I can actually simplify that and present that system to you, or the parts of that system that I think are important, in this diagram, and show you how from catchment to coast, rainfall and the timing, duration, volume of flows changes, how people need the water, how their utilization affects water availability, how they then are a part of the environment and impact the environment, and how people are a part of the environment. Not only is it important that people interact with the environment in a safe manner. One of the kids who I've showed this to before said, "Is he missing his legs because of the crocodile?" No, it's just to show you that it's very important that people interact with the environment. And then also if we consider how the environment affects people from a disease perspective. So we're trying to get this system balanced and make sure that the system is functioning. And in terms of sustainable water resources, it's our job to make sure that the balance between how we develop and use the systems and how we protect the systems is achieved. By the way, I can't see anybody's hands. If there's a very important question, please could you just interrupt me and just say, "I have a question," and then we'll answer your questions quickly. Okay, so please don't be shy.
That's fine, Prof. Gordon. I will let you know if there's a hand. Thank you.
Great. All right, so from the eco-classification philosophy, which was now dating back to 2008, and these manuals and the philosophy behind it is available, we understand that systems include control or driver aspects. There are multiple processes. There are habitats and the place where everything happens. And the ecosystem itself responds to all of these dynamics together. So in river health monitoring, we generally acknowledge the geology, the climate, the morphology of your habitat. And then you can see there's a little land use add-on to show you how that contributes to what's going on. That there are multiple processes, and if we can build and add and understand more of these processes, the better. But that all integrates all those activities. If you're a little fishy in the middle of a river somewhere, you're going to be exposed to and experience all of these impacts together, affecting you where you live in a habitat. And based on what the natural variability and dynamism of the system was, organisms and species and populations across our basins have established themselves. And we refer to that as our reference characteristics. So under natural conditions, without man, without our land use changes, for example, and abstractions, for example, our ecosystems have established themselves, and whatever's in those systems have the ability to respond to the normal natural cycles, droughts, wet periods, and other variables, interactions and competition amongst themselves. And that we refer to as the natural baseline characteristics. Now, we can't maintain all of our rivers in the whole region in a pristine natural state. It's not possible, because by us engaging in or interacting in or growing in our landscapes ourselves as a part of these systems, we're going to cause effect. We're going to use some of the water and that system's going to change. The question is, from the reference natural characteristics, how much change is acceptable and how much of that resource can we use for our own benefits, for the benefit of our communities and our ecosystem, our economies. So for the benefit of our people, the social benefits, their livelihoods, as well as our economies. And that's the challenge we're in. But in order to determine what the correct balance is, we need to always relate what we're doing back to what the system looked like naturally. And in the Limpopo Basin, we consider that most of the basin, or large part of the basin, is more perennial. And not only has it changed from a more perennial characteristics to being seasonal, that a lot of the rivers that are ephemeral, that only flow at certain times of the year when there's high flows, a lot of those rivers were more seasonal. They would flow more regularly than they do today. So if we know what it looked like, and we can get some idea of what used to occur here, and we can get some idea as to what processes were in place, we can then determine a vision as to how much change we think is acceptable in different parts of the basin, because there's some parts of the basin where we need to use the rivers more in harder, or we need to use more of the resources compared to other parts of the basin where we can protect our resources. And that's why with most of you in the field, we speak about the possibility of the Shashi and Dikhatlong and flows as a offset protected part of the basin, that we can try and restore some processes. The Nuanetsi, and how the Shashi and the Limpopo main stem and the Nuanetsi and connecting the main stem and down into Mozambique could become this future corridor where we focus on trying to or emphasize the protection of those environments while we're using the rest. Why? So that we can try and protect some of the biological and ecological resources for the future that might help us to then reestablish the condition of the rest of the basin, all towards a sustainable balance. Okay, so and again, I know, guys, I present a lot of information to you quickly, and I'm trying hard to get that balance right as well, to make sure that I understand where all of you are. I know that there's a bit of a language barrier as well. So I hope that with the recording, you may be able to slow this down a little bit. And if you have questions, please come back to us. Okay. So in terms of understanding this system, and we acknowledge that as a part of the philosophy for our river monitoring, we then have to decide how we're going to do this. Okay. So I mentioned the ecological references and reference conditions, and we know that there's land use, and we now have to identify what are the system drivers, the physical, biophysical characteristics of the physicochemical characteristics of the landscape that we're going to consider as our drivers of the environment. How do they then affect the environment? And what biological attributes of our system can we establish as ecological indicators? And this is the result of the argument, okay? So we know that water quality, hydrology, and habitat geomorphology are important foundational drivers of systems that we need to understand, and how land use activities and our use of water resources changes the water quality, the hydrology, and the geomorphology or habitat. How does that then affect the in-stream and riparian habitat, which represents our system? And very importantly, how do we represent hydrology in that physical habitat? How do we consider and represent geomorphology and habitat in that habitat that our ecosystem, our biological response components respond? And for the biological indicators that we've selected for monitoring, we've selected fish, aquatic invertebrates, and riparian vegetation. Now, in other parts of the world, there are other indicators. They've included microinvertebrates. They've included diatoms, and we often use some of these indicators to address specific issues. But these components, the water quality, hydrology, geomorph, and then in-stream indicators, in-stream assessment methods, as well as fish, aquatic invertebrates, macroinvertebrates, those that you can see with your naked eye, and riparian vegetation have been established as the foundational tools and components of the ecosystem that we consider when we look at the present ecological state of the system. Okay. Whew. It's a lot. So in terms of the eco status monitoring program, where we're trying to determine the current state of our ecosystem, as in that's what the eco status means, we use driver indices and tools, and that's what we've done in this study. We've got in-stream habitat integrity assessment methods, riparian habitat integrity assessment methods. Fortunately, because of this study, we are looking at environmental flows as well. So we have done geomorphological, hydrological assessments as well. So we've got additional data, but we focus then and we use the fish, the invertebrates, riparian vegetation to give us an idea of the in-stream condition, the riparian condition, and then that informs our ecosystem condition, our ecostatus. Okay, and that's a simplified version of what we're trying to do. Can I quickly ask if there are any burning questions at this stage? This is like a bit of a natural break. No burning questions. Is it okay? I'm aware of time, but I also want to make sure that I don't go so fast that you don't understand me. So can anybody just comment on whether it's okay and I can continue? Anybody? Everybody still there?
It is okay. You can continue.
All right, thank you. Yeah, sometimes, by the way, I'm sure many of you have experienced this, that you continue for another 10 minutes and you realize you're the only one speaking. So I'll just keep checking from time to time. All right, so this is the simplified way that we represent how we look at the interactions between water quality, habitat flow, invertebrates, fish, riparian vegetation, and how that's integrated into an ecostatus. And there's a tool, there are models that we use to do this. We don't just use guesswork, okay? So there's structured tools behind this that have been tested. But what's important here is, guys, the water quality affects all, the inverts, the fish, and the people. So if I use the water quality to contribute directly towards my ecostatus, I'm using the water quality once, and again through the eco-invertebrates twice, again through the fish 3 times, and again through the riparian vegetation 4 times. So if I used water quality to directly contribute towards my ecostatus, I would be double accounting and using the same information 1, 2, 3, 4 times. And that's why what we do is we focus on how water quality, habitat, and flow are affecting invertebrates, fish, and riparian vegetation, and then we require those results to contribute to my ecostatus. Okay, that's a very important understanding. And what it looks like, we use these ecological categories from A to F, and just to give you an idea that A is natural, unmodified, natural conditions, pre-development usually, or representative and comparable to natural conditions. Some slight changes for B, moderate changes for C, large changes for D, but still sustainable. That's important, is that our threshold of sustainability is between D and E. So even though D is poor, largely modified, the system is still, most of the processes are functioning. The biodiversity and the diversity of species is not significantly changed. There is some change, but it's not, we haven't lost the entire communities. There's still a lot of fish, there's still a lot of invertebrates. But when you slip into E, seriously modified is where you're on a slippery downward path towards unsustainability, and you're continuously losing species that may not recover. And F is when you've actually lost most of it anyway. So if you think of A to F, D is that worst but acceptable condition. And also consider that if you've got Ds in some areas of the basin, you can't have Ds everywhere, because in some areas you're going to have some Bs and Cs and or an A, so that you can get that balance on a reach scale or a basin scale. And again, that's where we've discussed the opportunity to consider, for example, the Shashi, the Nuanetsi, the Luvuvu in South Africa, and also the main stem down into Mozambique. That target towards higher ecological category will maintain more biological attributes and processes that can then contribute to the rest of the basin. Because if we lose all of them, they're gone. And then we will not be able to get them back one day. So even though Ds are permitted, in many areas, Ds are not allowed to occur for the whole catchment, the whole basin. And I hope that makes sense, that you've always got to consider among stakeholders in an equitable manner, considering the different countries, how to get that balance between hardworking areas, Ds, modified areas, not so hardworking Cs, and some protected areas, Bs and As. Okay, and then when we do it, if you look under natural conditions, As usually result in As and they give you As. That's what it generally looks like in the past, although it's not always the case, because remember, in the past you get droughts. So even under natural conditions, your condition may change from an A condition to something that the indicators, the tools identify as not being in a pristine state. Okay, and then if you look at another scenario, sometimes we get issues where water quality is fine, habitat is bad, maybe because of a dam or habitat removal or barriers or something, and your flow might be fine, but then your invertebrates are responding because of the habitat. Your fish may not be as affected. Your riparian vegetation may be responding. This may be a dam, for example, where you've lost habitat. And then your overall ecostatus using the integration model would be a C. So remember, even though you have a C as an ecostatus, it doesn't mean that your invertebrates, fish, and riparian vegetation are also Cs, and all of your indicator components are Cs as well. This is an example where sometimes the worst of these three variables affects your whole system. Okay, and we often want to communicate that. So we often focus on the ecostatus, but if you know that there's a problem with the ecostatus, the next step is to look at the indicators, invertebrates, fish, and riparian vegetation. And here you can see it's vegetation invertebrates that are responding, and then why they're responding. What's the problem? The water quality is not a problem there, that the habitat is, if that makes sense. I hope that makes sense. And then on occasion, unfortunately, we find ourselves in this situation where water quality is adequate, habitat is adequate, moderately modified, but not ideal. Flow is really bad. So the big issue we're dealing with is flow. Invertebrates are acceptable, riparian vegetation, and the fish are really responding in a poor way. They're really struggling. And if you integrate the information, you may end up with like a DE category, for example. And again, this is below the threshold of sustainability. Maybe your target would have been a D. And if you go back, you'll realize that it's the fish that are the biggest contributor to the DE estate. And why are the fish responding in particular? It's because of their vulnerability to altered water flows, hydrology, and you would then need to contribute and work towards improving the hydrology in that particular part of the basin. And that should then improve the flows. The fish would have a positive response, and you would then be able to recover back into a D category. This is how it should be used. We don't always find that it is used like this, but it should be used. I also want to then give an example of how people have used this in the past and what it looks like. And in South Africa, in different parts of the catchment, this is the Vaal. I'm going to show you some other case studies, just one or two others in a moment. But you can see they've got the desired health is fair. That would probably relate to a C or a D category. And the colors they've used are slightly different. I think they've used this as a simpler approach. It's quite old. But what's nice to see is you can see which components are responding. Where are the problems? When you see all these reds, you know that the skoon, which means clean in Afrikaans, so the clean spread, the clean river is the one that's really struggling, as well as this Mortar River over here. You can see that's really having problems. Upper reaches are not doing too bad in some parts. The fish are really struggling in most parts. There's a place where the fish is doing well. So it's nice to show you this because you can see overall, you get a quick idea of what's happening today, okay? Now, under natural conditions, they will all be green. And under future scenarios, you could consider how this would continue to change. You can even look at trends. But this is the idea of how to use the information and what you can do with it. Here's another example from the Letaba, which is a part of our study area, our catchment. This was also work that was done in the mid to late 2000s. And here you can see the desired health is good and fair. Some of them are natural, especially the lower Letaba, for example. This is in the Kruger National Park, and what the conditions were. And I tell you, which is so sad, is that in the mid 2000s, these greens were amazing. It was so nice to see there was so much going on. It's definitely not the case anymore, which is unfortunate. And then in some other areas, what do you need to do in different places? Okay. And you would unpack the results in a similar way. Here, you're only provided with the ecological response data, the invertebrates, the fish, and the riparian vegetation. In some parts, some of the indices weren't available. Maybe the river was a seasonal river and there was no in-stream water, for example, during the assessment. But then you could unpack the information and go back to what are the water quality, habitat, and flow drivers affecting that overall state. Yes, and then later on, we've now established, for example, these overall ecostatus for different attributes like fish, and then we can use this data. And guys, unfortunately, in large parts of Southern Africa, we've used our systems considerably or excessively. So we find ourselves often in these poor conditions. And it's up to us, really, to drag that back, to work towards restoring so we can get a better balance. It would be really nice to see more things like yellows and a few greens and yellows. That's really what we're working towards. And I think sometimes where this is being done, we're not documenting this, and it's a loss of an opportunity to show that in some places we're still degrading our environment, but there are examples, especially through the implementation of environmental flows in some of our rivers in the Kruger, for example, where we have seen some recovery. But I know that its resources are often limited and unable to do the work so that we can document the value of these restoration activities. Another example, I just wanted to show you how valuable it is to use this information and consider what's happening over time. This is from a case study in KwaZulu-Natal. There are not a lot of these case studies, but I wanted to show you because this is one where there's quite a lot of data. And here we have an indication of major events in 1985, these major flood events, 1985 and 1987. Then the first reserve determination was achieved in 2003, and that reserve determination target was at a BC ecological category. In 2018-ish, I think, an update was done, and that's still supported the argument of a BC target. It may have been a bit lower, but there was some target for a BC in the area. So in terms of health and natural down to unsustainable, here's our limit of sustainability, as I mentioned, the difference between D and E. You can see we've got a vision to get it up there, okay? These are different groups, by the way, who did a lot of the work, the sampling work. And you can see that in the 1990s and early 2023, the system was in a BC category. This is the black is for the estuary. The black is the Tugela River. The blue is the estuary, and the white is the small stream that was heavily impacted by industry. And you can see, I just wanted to show you the value of data over time, that you can see these trends. And when you see things like this, you know where it's going, and we really need to claw it back. And here's an example here. Even though it only recovered from F to an E and almost got up into a D, some of the industries closed and or changed their processes so that it almost got back up into a D. And this is just valuable to show stakeholders where we've been, where we're headed, and how you can contribute. And we really want to see, we know that it's a reality, which is the hardest tea to swallow, that we need to use our resources. But together we need to work towards bringing these back up and getting them back towards these visions. We need to figure out how to do it. When doing reserve studies, I'm almost done with our introduction. We need to consider other information. And this is where the National Environmental Management activities in South Africa have got protected areas, buffer zone areas, Ramsar sites, and other areas of conservation value. It helps you understand where you've got a particular present ecological condition, what's important, and why it is important to consider the Makuleke wetlands, for example, in the floodplain, and the other reserves, and we've looked at that already. There are other processes in South Africa, including, for example, the present ecological state, ecological importance and sensitivity assessments that provide a lot of really valuable data that you can use as foundational information for assessments. And we encourage people to look at what's available. Often, unfortunately, a lot of these assessments are rapid, and the specialists don't have the time to go and look at other available information. But we advocate it and as best or good practice, and we really encourage you to try to collect as much evidence as possible to understand what's going on and where are things happening. I also wanted to highlight the importance of looking for and using published information. Fish and macroinvertebrate assemblages reveal extensive degradation of the world's rivers, and that there was a South African data incorporated into that, but there's also often data from publications from Zimbabwe, Botswana, and Mozambique. And we're contributing to those publications, so you should definitely look out for them and use them. South Africa is doing the national biodiversity assessments. Zimbabwe and Botswana and Mozambique have different reporting requirements to report on the state of their environments. Contact the reserve managers, find out from them what they know, and then you'll get a more holistic representation of the overall present ecological state of systems. Just quickly, when you look at these other considerations, it's very important to look at the nature of the rivers that you're monitoring and classify and make sure that you know that what you're monitoring is a river, and that you'll be surprised at how a lot of these tools are abused, and that the tools are being used adequately or as they have been developed. Understand the difference between the upper reaches and the dynamics of your river environment in the upper reaches. the middle reaches, and really areas where there's rocky and diverse habitats. These tools are very robust and comprehensive. In smaller rivers, wadable rivers, and then as you move down towards, this is just some indication of impacted and altered rivers, artificial environments. Can you apply this tool in an artificial drainage line and call that a river and do an assessment and contribute to river health monitoring? I don't think so. So you need to be careful with how you apply it and where you apply it. And then as you go down to lowland rivers where they're more alluvial, which is what we're dealing with, some of the tools applications are not as confident and as robust as they should be, because by not having rocky habitats, for example, you're excluding some of the components of the models and the indices that have been designed to give you a more confident answer. So what we do as a result to offset that uncertainty is we add additional data to try and have a better understanding of what we do. And we're going to show you some of that today. And in terms of floodplains, this is right at the lower end of the study area. It's very difficult to sample these habitats the way you would sample these upper rivers and streams. So the methods that you use and the application of the tools are affected by how confident your sampling could be, and just to make sure that you represent it correctly. This is a picture I love to show people where it's important to also understand what's happening in the environment. So this is a reach of the Crocodile River in the Komati Basin, where within 30 minutes of these pictures were taken 30 minutes apart. So you can see here, based on the facility, we closed the gate and allowed water to flow over the weir. You can see here at the bottom, the water flowing over the weir is reduced, but then this channel here is flowing strongly, where 30 minutes before it was almost dry. And if you then do your assessment, you will get very strange results. And that, I think, is something that we observed in Gonorrhoea in the Nuanetsi, when we sampled quite soon after the flows had started to increase again after a dry period. Okay, so you need to understand that. Also, don't go and sample when systems are in a state of flux and there's high variability. This is the same site. You can see the weir, same location. First of all, you're not going to be able to sample here effectively. Secondly, the whole system is in a change. So if you want to apply the standard river health monitoring tools, they're not going to operate adequately here. And when you're comparing the reference condition, you're not comparing to a reference condition during this abnormal flow period. You're comparing it to a normal based flow period with a stable environment to a system that's in a flood or freshet state. Okay. I also added these two pictures of Annalise when we were together in the Limpopo. I was with her, so it wasn't too unsafe, but be very careful of other dangers of drowning and events like this occurring. And please be very aware of the wildlife and the danger that you have of wildlife. This is a picture of the rangers who were attacked by a hippo in the Kruger National Park. And that's something that we're always aware of, is your precautions. Okay. As I mentioned, you can look at other tools to complement what you're doing with river health. So even though there's a minimum requirement and foundational requirement for you to work with, there are new methods and techniques like environmental DNA that you can add. This is Prof. Matt Gruel, who worked with us on some development of our work, and we're doing some of this now. There's also very valuable databases for historical data, and we encourage you, for example, to go to the Freshwater Biodiversity Information System that's available, and you'll see that there is information for the whole basin, much more in South Africa, but we're hoping to change that our data and your data will improve our understanding of the basin and other areas. So we encourage you to use that. Application of the data in ecological reserves and reserve determination studies across the region. Share the information, because with the information available, you'll be able to make a better contribution. Dr. van der Waal is going to mention geomorphology, but a lot of the foundational principles we understand and we consider, like at what velocity does sediment start to become, start to move, and how can we use that to understand what we're doing. We also look at information from communities. So this is in Mozambique, where we have opportunities to see alien crayfish, alien species, alien tilapia or tilapia that they're catching and using. We might not catch the eels that they catch, for example. And this is actually from the Sabi River upstream of Kruger. some local communities can target fish migrations, and they'll have information for us as well that we can use. All right, that's the end of my site selection. We're going to move into have a quick look at our sites, which is only going to take a few minutes. And then we're going to move on to a geomorphological presentation to demonstrate how we approach one of the physical components today. And then I think we're going to move on to Angelica to do some of the fish stuff, and that's what we're going to get to today. So I'm just going to jump ahead quickly and just show you that these yellow sites are the sites that we went to during the first survey. The red sites, the red triangles are the ones we went to during the second survey. The orange ones here are the ones that we're going to go to now soon, this season in Mozambique. And we have a lot of additional data from South Africa, and we estimate that we're going to get to about 40 sites to represent the whole catchment area. And then we have data already to show you how from the upper, more arid reaches of the basin towards the middle reaches that are more perennial, and down to the slow-flowing, sandy alluvial parts of the lower part of the basin. That was also the Booba River. I'm not going to go through this because I presented enough of it. I may get to it next week. So, Dr. Van der Waal, are you able to share and present on the geomorphology?
Yeah, Gordon, I can do that.
Okay, Prof. Gordon, maybe colleagues, after this presentation from Prof. Gordon, do you have any questions, any points of clarification from the presentation before we proceed to the next one? Please feel free. Yes, go ahead, Botswana. I don't see any hand, Prof. Gordon. So I think we can. Oh yes, please go ahead.
Professor Rugara.
It's good to see you, Prof. Gordon, and the team. Compliments of the season, and I hope we are doing well where we are. Just to mention to Prof. Gordon that he still cannot pronounce Mwenezi. He still calls it Nwanezi.
It's one of those things.
It's the Mwenezi.
Thank you. No, thank you. Please don't stop correcting me. I'm trying to learn. Yeah.
The question is, it builds on the philosophies you were presenting of using ecostatus to determine the river health. I think when we look at it from the perspective of how we implement things here in Zimbabwe, it becomes a very fascinating approach. How easy has it been for you in South Africa to at least bring all these components together and then come up with one point, which is your ecostatus, that you then use to monitor the health of your rivers? Just your thinking on how the steps that you've gone through as South Africa and how other nations can learn from that. Thank you.
I think just a few comments. I believe, and I'm sure my colleagues can support me, that in the 1990s and early 2000s, there was a lot more interest and opportunities, development opportunities, resources for river monitoring. And I showed you some of those big maps where whole basins were being assessed and evaluated. We have in South Africa experienced a rapid development of methods and application of those methods and support for the methods from multiple stakeholders. So I think that's where in the 1990s and early 2000s it was very successful. It wasn't a top-down government-driven process. It was supported by industry and land use activities, by users. It was supported by universities. It was supported by conservationists. Many people were working together towards developing methods and determining the health of systems and using the information. And we've, for many reasons, including resource difficulties that the whole region has experienced from, I'd say, 2007, 2008, from those recessions, how we've noticed how the amount of human resources is declining, financial resources is declining, but the methods are still improving. So the opportunity to use the methods and build on what has been done already, stand on the proverbial shoulders of giants, is available. We need to redevelop the value that stakeholders have, including formal stakeholders. Now I'm talking about regulators like the Department of Water and Sanitation and Environmental Affairs, for example, in different areas, for standing and wanting to know what the health of the rivers are and then what to do with it. So not only do you need to know that you're getting C's and D's and E's, but then what are you going to do with it? What are you going to do about it once you have it? And that's very important. So I think that look at South Africa's lessons, and we can talk about this again one day. I think on a LIMCOM scale, it might be valuable towards the end of the studies to say, we've got all this information now. It's unrealistic for us to expect it to result in changes on the ground immediately. It's not going to just be better. It's not going to just cause anything to change. What do we need to do to start to build our own capacity, start to use the information ourselves, start to manage land use better, start to establish these protected areas, start to contribute towards long-term monitoring, and then we will start to see the benefits. And we will also start to get more buy-in, because I'm an advocate of, I love it when my little African map pops in. I don't know how or why, but it does. But I'm an advocate of, if you can show stakeholders success stories, people buy in, and then it grows and grows and grows, and everybody wants to be a part of the success. But if we take a stick approach and we just hammer people forever, and we don't also try to give them the carrot, give them something to work towards, it's not sustainable. It doesn't work. It starts, there's resources, people come in, and then it goes. So I don't think there's a clear best practice approach to do this, but the fact that LIMCOM now is starting to bring stakeholders and communities together, that they've reignited, because this is the first time we're doing this on a transboundary scale, that we're trying to get all of you together to look at what could we do and how are we doing it and what has been done and what's the best approach. That is exciting. So I actually think we're doing it now. I hope that there's buy-in from the stakeholders, the riparian states, to continue to develop. And if South Africa, if I would love to see Zimbabwe take over and exceed from what South Africa has started, and to continue to develop the approach, and also to get a really good understanding of the health of their rivers. It would be wonderful to see the other countries really progress and then pass what has been started here, and or for us to share resources together to start to spread the importance of and the knowledge for what's not only going on in the South African side. It's very sad to see those maps. I always show you those maps where you can see the border so clearly, because all the work was done. As soon as they got to the border, they stopped. And that would be nice to see changes. So there's a couple of recommendations, a little bit of a background. I hope that helps. A lot of work to do.
Yes, go ahead, Botswana.
It's Benny.
Oh, it's Ben.
Benny.
Okay.
Yeah.
Yeah, thanks, Gordon.
Okay, let's proceed.
Gordon, you've seen a few of the tools that are used internationally. Are we on the right track in Southern Africa, or do you think it's time for a revamp, or do you feel what we have is robust and good enough?
That's throwing a snake amongst because the world is starting to do different things. And for example, in the West and in some of the developed worlds, they are not using invertebrates at all anymore. But it's because they've replaced the use of invertebrate community structures as indicators with high-tech fish indicators and tools. They're using really fancy things. And I think I think that there are lots of other methods that are globally very exciting, but a lot of them are very expensive, and it's not realistic to think that we can do that here yet. So I think that what we have is more than adequate for us to at least determine the present ecological state. I think that if I can add anything in terms of best practice, it would be to not lose the actual evidence itself when you do these assessments, because what often happens, so this is the one thing I would advocate, and we're going to write this up in our report, is that we've realized with trends and river health monitoring over years, is that if you just get C's and C's and C's and D's and E's and C's and D's, and you then say, okay, what actually changed? Where was the water quality issues and how did we change it? That information is not available anymore. What part of the fish community was in a poor condition, and how did you address it to result in change? And that data is not available. So all that's left is a C, and I can't use that data. And I think that's something that we really need to advocate as good practice here, is that descriptive information, the evidence, the real evidence to say what's behind that C and what's behind that poor state assessment of water quality. It was a toxicant, it was a nutrient, it was we need to hold on to that science, that evidence. And from a cost benefit, it's high that we do that. We found now that the Kruger Park, SAPI, many stakeholders are wanting to start to report more on populations of species and their trends, and long-term quality dynamics, not just a score. Do we have endangered species and how are they doing? So they're naturally maturing and needing to monitor more than just the foundational river health. So I think this is a good platform, but there are lots of low-hanging fruit that you need that can make a massive additional contribution to the monitoring. And we think that a future balance between a little bit of science, understanding your yellowfish as indicators, or paper mouth in America that we all saw together, and then having the categories and the tools and the results of the tools and the evidence is probably good practice. Sorry, that's a bit of a long-winded answer, but that's our job, is to try and make you as aware as possible of the advantages and disadvantages and new developments and what best practice looks like today and may look like in the future, and that we will report on.
Oh, thanks. That's good.
Okay, Benny, can you continue with your presentation? We're running out of time. Let's see how we do. We might end with this. Okay, go for it.
Yeah, good morning, everyone. I'm Benny van Waal, and I'm doing this work with Nick Hoeksemeyer. He's also in the meeting at the moment, and a lot of you have met him in the field. So I'll talk a little bit about describing physical habitat and how that relates to geomorphology. And then, as Gordon said, it's important for us to keep a good record of what the bed sediment type was and what the level of embeddedness was, because we can then explain some of these trends that we see in terms of what the fish are doing and the invertebrates are doing and the vegetation is doing. So we're not just doing this to keep us busy. We want to understand this basin, build up a picture of what it looks like across the basin, the diversity and the changes in the physical habitat. And then once we start monitoring it, we can obviously use that to inform our adaptive management. So here we have a long profile of the Limpopo River. It's odd. It's not what they should look like as we see in textbooks. Normally you have this kind of shape. You've got your headwaters here and you go down to your coastal plains where it's flatter. But in the Limpopo River, we have all these tributaries coming in, and we see this very flat part at the top here. So that is quite odd, but it's all to do with the evolution of Africa and the geological makeup and some of the historical drainage networks. So the Zambezi was thought to drain through the Limpopo, and that is one of the things that is driving this. And it's also because of continental uplift, so you've got river rejuvenation. So the rivers at the top here could have a character that's very different than what you would expect. You can have lowland rivers right in the headwaters here, and that's what we often see. So this is a map of some of the main river styles. So this is a bit of an Australian classification system, but I do think it's useful. So the sections in red, you can describe as bedrock, rapids, and deep pools. Whereas green is more of a wandering or sinuous river with mainly a sand bed. And your black is your low sinuosity river with floodouts and very fine sand. So we'll find the highest habitat diversity in these areas that are red. And we can see there's a nice spread throughout the catchment, but some of the rivers do not have a lot of that. So we do need to think about what we expect in terms of some of the fish and some of the invertebrate species in them. But we also need to think about how we can keep connections between these different reaches going, because that's important for the biota to be able to move between them, and for us to really look after these areas of high habitat diversity, because we don't have a lot of that across the basin. And then just in terms of sediment types, we have our dissolved sediment. So that is the stuff that doesn't taste nice when you drink the water, your salts and so on in the water. It can indicate chemical leaching from things like rock types or from agriculture where you have a lot of irrigation. And obviously, some of your industry and wastewater that comes into the system. And it's quite easy to monitor. We can use an electrical conductivity meter to get an idea of the quantity of salts in the water. You also have your suspended sediment. So that's sediment that's in transport during high flows in the water column. So it's basically from clay to sand size. And it indicates surface erosion. So if we have a lot of mud in the water, like we see in this photo, we know that this catchment is bleeding sediment. So instead of keeping the sediment on the landscape, it's being mobilized and it's moving down the river system, and we're losing it. That soil is never again available for cultivation in this catchment. And by the way, our soils in Africa are very old. They've developed, we don't have a lot of soil. The soil layer is quite thin, and it's developed over the last it's millions of years. So if we lose a millimeter of soil, we cannot build that soil up in possibly 1,000 years. That millimeter takes a long time to develop. So what we're trying to say is that we need to keep the soil on the landscape. It mustn't come down the rivers, and it mustn't be pumped out to sea. And then we have our bed load, which is our larger particles, so sand and coarser. And that is important because it forms the physical template of our habitat along these rivers. So in the field, what tools can we use? We can use our cameras. We all have good smartphones, so we can take really good photos. We can use drones. They're becoming more accessible, and they are fantastic for getting an aerial view. And what is important with photos is to take time-lapse photos or fixed point photos. So you go to the same point, you have the same angle, and you take a photo of the same landscape every time you go back to the site. And then over time, you can build up a bit of a picture of how things are changing and what management strategies are working. And as we mentioned, to keep a good database of that is available to people in the future, that is very important. We can use simple tools like a tape measure or calipers to measure sediment size. I'm sure a lot of you saw the sand ruler in the field. It's a very simple disc with different sand sizes in it, and that gives you a quick idea of the sand size that you're looking at. If we want to take samples to a lab, we obviously need bags and tools to collect the sand with, or the sediment with. And then if we want to do cross sections like this, we need quite accurate survey equipment. So that is good if we do repeat surveys to see whether these different features are changing in elevation and also in their extent. So if we combine that with good aerial photos, we can confirm that if we lose all the inset benches, that we have a lot of bank erosion, and that we can then see on aerial photos as well that it's quite extensive. So we know, listen guys, we have a problem with bank erosion in this catchment. how can we manage our flows differently, or how can we encourage vegetation to stabilize these features, maybe by restricting grazing to areas outside of the riparian strip. So diverse habitats are very important. So this is a typical cross-section of a Southern African river. So you have your low flow channel. So this is where during your drought or dry periods, your winter time, your water is concentrated. So that is the only habitat that's available to your biota during those periods. Whereas as you go into your wetter seasons, you start inundating these bars and these inset benches. And during your higher flows, the water can be up here. So you've got nice slow flowing water with vegetation where your biota can find refuge during these high flow events. And then we have a nice way to describe the different sediment types that we see for these different habitat features or geomorphic features. So if we use some of these analogies, it's quite easy to go into the field, look at these things, feel it with your fingers, and get a good feel for what we're actually talking about. Then also, from a geomorphic point of view, we work across scales. We work from a catchment scale to a valley scale to a kind of a planform scale, and then really zooming into your sediment types. So it's quite important to know what type of valley setting we're in. Something like this will obviously have very narrow flood benches. So when it is flooding, you've got limited habitat there, compared to something like this lower down the system where you've got these extensive floodplains that can trap a lot of sediment and provide these ecosystem services that we often after. And then also to every time you go to the site, just to check, is the planform type still the same? And we can also look at this on historical photos or satellite images that we can go back in time to see, is our river changing from a gravelly kind of straight system to something that's more braided? If that is the case, then we know you normally have braiding when you have excess sediment. So then we get an idea of how our drivers are changing. And then we can go up into the catchment and see, hey, where's all the sediment coming from? Is it from changes in land use, or has someone closed or built a new dam and that's taking the water away so the sediment isn't transported through the system? So then we can go back and figure out where these changes are coming from and what is driving that. And then also something like embeddedness. So ideally you have spaces between your larger particles, sediment particles, where your invertebrates and your fish can hide. If you have a lot of catchment erosion, you're going to have a lot of fine sediment throughout your year, and that sediment is likely to settle out, and that will then be deposited between these particles, which means that the housing that this habitat should provide is not available, and that then drives change, ecological change, which we will pick up. But the habitat quality can inform why the biota are responding in a certain way. So just in terms of connectivity, so there are two main drivers. The one is flow and the other one is sediment supply. So if we do see changes to our habitat, we need to go interrogate these two drivers first. And a good way to do that is to look at landscape connectivity. So there are four different things we can look at. So the one is changes in longitudinal connectivity. We also have lateral connectivity, so from your channel onto your floodplain and back in. Your vertical, so your groundwater or that water just below the channel. We often have these alluvial aquifers. So how do you has the connectivity between your alluvial aquifer and your channel changed? Because that is quite important in times of low flow. And then also your hill slope channel connectivity. And these different dimensions can change over time. So if we can describe this just by driving around the catchment, we can understand some of the things that we see at the site. And those can be things like increases in gully erosion, increases in roads, weirs and dams that are being built, these barriers that we add to the system, and things like clay. If we have a lot of clay depositing in our system, we reduce the conductance of our riverbed. So that means that less water can infiltrate into that lower alluvial zones underneath our river channels. So when we have good photos of the site, we can then start describing the different habitats. So here we have our floodplain, often with fine sediment. And then as we move into our river where the flows are faster, we often get coarser sediment. And if we have a good snapshot like this, for every time we go into the field, we can quickly start seeing changes where we suddenly clog these habitats with sand. Then we understand why suddenly we're losing a lot of fish and invertebrate species, just because this habitat is no longer available to them. So good photos are key, and also to store them in a good database so they're accessible. Also land-based photos, so using our smartphones, we can take some really good photos of different habitats in the channel, the sediment makeup, and then also, some of the in-channel features, what is inundated, what is available to biota, and things like bank erosion and trampling. It's always good to have a good feel for that. And then we can describe the different features that we have. So here we have our bank, sand and gravel on the bed, some of the deposits, the larger stuff, and then our other bank. And here we have the different sediment types, the dominant sediment types. And based on the measurements, we can actually work out the median particle size. And here we see it's a particle that's 0.3 of a millimeter. So then we can classify it and we know it's a medium-sized sand. So every time we go back, we see the left bank, has anything changed there? Is the sediment getting coarser or finer? Because that would also give you some bearing on whether the sensitivity of those banks to erosion are likely to change. We can also score the embeddedness. So that's the extent to which the pores between the coarser sediment is filled by fine sediment. We can also look at packing. So if the stones are packed like roof tiles, then they're quite immobile. So they'll be very insensitive to flow, mobilizing it. So that could be a bad or a good thing. We can also look at sorting. So if we have poor sorting, we know that the hydrograph is quite a steep hydrograph. We don't have a nice period after a flood that is sorting the sediment into different sizes along the channel. So if we have poor sorting, we know that it's a very short flood event and it's basically just eroding, mobilizing a lot of sediment and dumping it. So those are all things we want to keep an eye on, so we understand how the physical habitat is changing over time. So by using the survey equipment, we can get a good idea of the size of the different features and their elevation. So if we repeat those surveys, we could get an idea of whether the system is aggrading or degrading, so being eroded down. We can also map the different sediment types on it. So that is good, and where we have vegetation. And then we can also use this to inform how much water we need in the system to inundate some of these habitats. I'll get to that in a little bit. So here are some of the levels. So during our low flows, we might only require water to be in these channels on the sides here, but we do need to think about some of these geomorphological processes that we want to drive. So we actually do want erosion, we do need transport, and we do need deposition. And why do we need it? Because the biota and the plants, they need new habitats. If you only have a very static system with no erosion, they're going to run out of space to propagate their young. So we do need habitats to be eroded. We lose the adult plants that were there, and then we should have some deposition in that same area or similar area, and that is obviously a new habitat for seeds to germinate, for a new cohort of vegetation to come through. So that would also be good habitat for invertebrates and fish to come and colonize or to come and use. So these processes are not always bad. Bank erosion, We do need some of it, but we can't only have bank erosion. We also need deposition. So we do want to balance those processes. So when we do set flows, so one of the things we do is to look at the physical features that are there. And then we use that to pick out these different levels. So you might be interested in inundating some of these gravelly areas here with vegetation on them, because that might be good for fish breeding. So we do want to set a level that inundates that. But I also know that to move sand onto these areas, I need about 30 centimeters of water to flow over it. So that's how I can set a level of depth that I need to inundate those features and put new sediment on those features. So we can then relate that by using hydraulics to a discharge level. Also some of the higher levels, so we've got these little nice vegetated benches on the side here. We can set a level to inundate that, and then also some of our higher flood features. So we can relate these back to specific flows that we need during the wet season to drive some of the erosional and depositional processes, not just in the main channel, but also along the edges, because that is important for nutrient cycling and for developing new habitats. So this is now getting into the hydraulics. So we use 1D hydraulics. It's quite a simple, robust method to relate the depth in your channel to a discharge. So we develop these rating curves, and then we can say, okay, I want a depth of 1 meter to inundate those benches along the side, and I can then read out a discharge. In this case, it might be 8 cumex, and that's then the value that I use to say, if we can have a value of a discharge of 8 cumex over 2 or 3 days, we're likely to maintain these inset benches. The same for your higher features. They might be at a higher elevation in your channel, so we can pick out the discharge for that. And yeah, that would then also give us an idea, so we can use the hydraulics to spit out these different velocity depth classes. So that is important for your invertebrates and your fish. So they are dependent on some of these different depths. So we've got our shallow and our deep habitats, and then this is your velocity, so slow velocity, fast velocity, and then your different depths. So we want a nice range of those habitats. Remember, we need a diverse habitat to support diverse biota. So if we have a good range of these different flow depth habitats, then we know we can sustain some of these biological species. And that is obviously dependent on having a channel that has different features. If we only have a square channel that's very flat along the bottom, our diversity in terms of habitat flow classes would be very limited. So this is what the output from HabFlow would look. So that's the software we use to break that cross-section into different pockets. So it would pull out these very shallow habitats that will experience slow flow. It would basically split the channel into those different habitats, break it into those habitats for a specific flow level, and then show those habitats in terms of percentages. And if we plot that as we step up the level in the river channel, so this is how the water level is changing in our channel, you can see how the habitats are changing. So if we have a very shallow river, we obviously have these shallow, slow-flowing habitats, whereas you can see some of these deeper, faster flows are coming in as we add more water to the channel. So this is quite a handy way to look at different habitats that are available for our biota, and that is driven by the geomorphology, the physical habitat in our channel as well. So the flow in the river and the physical template in our river, they're working together to provide these different habitats. And then the other thing we want to do is to maintain the diversity of sediment types. So if we only have sand in the river and the sand is covering everything, we're in trouble. So one thing we want to try and do is to, if we do have gravelly and cobbly habitats, we want to mobilize those several times a year to get some of the fine sediment out. We know if we can have velocities that will start shaking and moving these gravelly type of sediments, we're likely to erode the fine sediment from between them. So one way to do that is to look at the velocity. So here's our flow velocity. And if we take our sample, we measure the stones, we can plot it, and we can work out our median particle size. We can use that particle size then to go and work out what velocity we require to get into that zone of erosion. So here we have our different particle sizes, so very fine up to quite large things, so cobbles and boulders. And here we have our velocity. So we see that, you need quite fast flows. So flows of maybe 0.3 meters a second to start eroding sand. Whereas our coarser sediment, we know they're more stable, so they will require velocities of maybe 2 meters a second to start mobilizing them. So that's one way to say what velocities we require in our channel to start mobilizing some of these coarser materials so we can clean them up so they're available for the biota. And we do get, in our head flow output, we do get some of those velocities, so we can use that then for a specific depth or a discharge to work out what flows we need to look after our sediment diversity in our channel. We can also go more complicated, and that is to use some of the physics, so shear stress, to use the same thing. So we have our particles, we've measured them, we know what the median size is. We can then use the formulas that are available to work out what depth of water we require. And we go back to our rating curve, and we can say for that specific depth, we require a discharge of X to get a specific particle size mobilized. And yeah, this is the last slide, just to bring it all back to what we're trying to do. We're trying to manage these systems in a dynamic equilibrium. So dynamic rivers has a bit of change over time, just because of changes in flood magnitude and events that can take place in the catchment, like veld fires or big rainfall events. So we do expect some changes in sediment type and size, but we do want to make sure that in the long term, the system doesn't just move in one direction. So this balance is quite handy. It's called Lane's balance. And we see here we've got the two main drivers. So we've got sediment on the one side and flow on the other side. And what this balance is trying to say is that the amount of sediment coming down the system and the median size of the sediment should be in relation to the amount of water that's coming down the system and the slope of the system. So that's a bit of an energy factor on this side, and this is the sediment supply side. So what it is showing us is aggradation and degradation. So if we make the one side heavier, this side heavier, it will push it towards degradation. So if we add more water to the system, it's likely to degrade, to erode the channel. Whereas if we take water out of the system, this will be lighter and it will push the system towards this aggradation, which will then obviously build up sediment in your channel. So this is a handy model to go back if we do monitor change. If we see the system is just cutting down and cutting down, we can use this balance as a quick conceptual framework to say, listen, our system is cutting down and cutting down. What has changed in the system? Are we not delivering the sediment? Is there a dam upstream that's trapping all the sediment and it's not coming down the system? Or is it that we've now put a big interbasin system in from the Okavango River or the Zambezi, and we've doubled the amount of flow coming down the system, and we have too much energy to transport sediment, and it's just cutting down. So this is a handy conceptual model to go back to try and understand some of the basics of the drivers and also what we monitor in our system. So yeah, I think that's where I want to leave it for today. Just some of the things that we can monitor along these river systems and how we can look at the changes that we observe and try and link it back to processes in the catchment and also things that we can control, things like land use and how we use our riparian corridors. Because that's the only way we can look after these river systems is by addressing the drivers along these systems. Thank you. Are there any questions?
Thank you,
Thanks,
Benny,
Benny.
for the presentation. Colleagues, there you are. Do you have any questions, any points of clarification from the presentation that has just been made by Benny? If not, I'll back to you, Prof. Gordon.
Yeah, thank you very much. And I think we've run out of time, and I think we're going to stop here because this is a series that we don't want to overwhelm everybody. So thanks, Angelica. I'm sorry she had prepared, but we're going to shift her presentation to first up next week. But this is the point. The point is to start to introduce you to the approach and the philosophy behind river health and the physical dynamics that we consider when doing these assessments. So you can imagine how valuable this information is, the geomorphological information is from specialists to be able to understand what we're finding in the field together. And the point of this capacity building is to show you we went into the field, we made all these observations, we have this data available to us now, and what do we do with it so that you can understand how we get to the outcomes that we get to, what we get to. So Zwiko, thank you. I think unless we have a few moments for one or two questions, we'd like to end it here.
I
And then-
see Dr. Dick. Please go ahead.
Thank you, Prof. Gordon. Thank you, Zico. And good morning, colleagues. Mine is just, I want to appreciate in the exercises through the joint basin surveys that how much do you include the citizen science that is involving the people who live within the river systems to also be part of the monitoring, those that will help actually to take care of the rivers. So I just want to appreciate that one, if it has found a place for inclusion or integration into the expert science. Thank you.
Great question. That's a great question. Thank you. And I was quickly trying to find the photograph, but I'll probably show that to you next week, where part of what I presented was we need to understand how the system's changed over time, and we need to get as much information as we can about what's going on. So we rely very heavily on local communities, and I was so grateful for the Mozambican assistance we had on the Elefantes River, where colleagues went and fetched a whole bunch of fishermen, and how we got all the fishermen together and we sat and spoke, and they explained species, they explained biology, they explained migrations, they explained impacts, they explained so much, and it really does change our understanding of the system. And what we explained to them was, because they would ask us, why are you doing this? And we explain that it will benefit you if we manage these systems in the long run. And then they ask, how will it look? So we explain, changing the amount of water that's available, changing the chemical characteristics, people caring about the system and what it could look like and how it could benefit. And they're the ones who benefit directly. And so definitely, Dr. Dick, because some of those communities, especially using Mozambique as the example, they were the ones who explained when they run out of resources from the river, it's so bad for them that they must leave. If we could just make it easier for them to stay there for longer, it would be very valuable. So I think that's a very important question and an important consideration that we have, that we acknowledge and that we raise to stakeholders and the rest of this community here, that we must never forget that the people we're doing this for are the people who are totally dependent on the systems day by day. So definitely we do it as much as possible. And in some cases, we actually include formal social components where we rely on communities. And that was done in 2021, by the way. So there's a lot of additional social information about what people require. We're going to use that information in this round and update it where we have new information. So definitely. In terms of your eyes and ears on the ground, I also advocate human communities to be very valuable to the managers here. And I know that from all of you, some of you, I really appreciate Mr. Pule and Alphinios as well for getting me those wonderful videos of the rivers flowing. And I know that you have people in the field that you call and you speak to. So it's there. Well done. Thank you.
Thank you, sir.
Okay, colleagues, any more interventions from the colleagues?
Zvika, I think we're going to leave it there for now from our side. Yeah, so just any more last comments? It's getting a bit late, and I think that we're looking forward to getting started with components first up next week.
Okay. Thank you very much, colleagues, for attending this session. Just a reminder to say that we are going to have these sessions every Thursday from 9 o'clock to 10:30 as indicated on the program. Let me now hand over to the program coordinator, Dr. Eddie Riddell, to give us a few words and close this session.
Thank you, Zviko. So I just want to respond on 2 technical points before I close. So in terms of Dr. Kenny's question around the citizen science, we're also pleased to announce that from the energy raised under the Joint Basin Survey, there is now a collaboration in place with the International Water Management Institute under funding through a program called Enable. And that has a very strong citizen science focus, and that will be a key collaboration for this year. And then also linked, because of this particular work led by Prof. Gordon, there's now a focus on the environmental flows side of things. So there will be revisits to the environmental flow sites this year, working with the member state representatives. And again, that gives an opportunity to, again, sort of capitalize that citizen science aspect around those e-flow sites. So we'll be requesting support from the member states in that respect as well. Yeah, so watch this space. And yeah, I just want to say thank you very much to Prof. Gordon and his team for a very well prepared and executed presentation. I think this is going to serve as a really good learning resource for future reference, both for the JBS team that is in this call and others that weren't necessarily able to be part of the surveys, but also just to be able to access the resource in the future. So we will be uploading this onto the LIMCOM YouTube channel shortly for future reference. So yeah, colleagues, I just want to say thanks once again. This was a great session, and I'm sure over the next month we'll be having really more insightful sessions as we go into the detailed sort of data analytics side of the Joint Basin Survey. So thanks once again, everybody, for attending and being part of this and interacting with the process and essentially owning the LIMCOM or Limpopo Joint Basin Survey. Thank you. I think with that, I will close. Thank you.
Great. Thanks, everybody.
Okay, thank you, colleagues. I think we have come
See you next
to
week.
the end of this session. So we see you next Thursday. Thank you.